I am Arup Bose from the Indian Statistical Institute, and I am going to talk about high dimensional random matrices. So, what is a random matrix? Very briefly, simply put, a random matrix is a matrix all whose entries are random variables. There are many examples of random matrix, in particular from statistics. I am not going to focus on other areas of science here, but focus only on statistics. For example, if you recall the 2 by 2 contingency table that all of us are aware of, that is of course a most simplest example of a random matrix. Similarly, you can think of the sample covariance matrix. You can also think of the sample autocovariance matrix, which is useful in time series. And you can, for example, from a design of experiments, think of the random design matrix. So, you can see that there are a lot of different areas of statistics where random matrices have already been existing. For the last 2 decades or so, these random matrices have turned out to be major areas of research and applications in actually many different branches of science. For example, you can if you think of statistics, then in the areas of statistics, the multivariate analysis, the linear models and design of statistical experiments, time series would be 3 major areas where random matrices would be existing: physics, computer science and mathematics. Of course, in this talk we will be more focused on random matrices in statistics, but there are, as I pointed out in this slide, there are other branches of science where random matrices have been used. As we all know that currently high dimensional data is a very important area of statistics, and in high dimensional data the usual procedures do not perform very well. So, for example, all the classical statistical procedures that are used for fixed dimensions do not go very well when the dimensions are high. High dimensional matrices come up naturally in high dimensional models. Properties of high dimensional random matrices are crucial. For instance, to understand the failure of the standard procedures and also to suggest new methods and applications. So, if you are thinking of random matrices, then what do we study about these random matrices? Any matrix is a linear transformation. Its features are captured by its eigenvalues. So, we will give a brief glimpse only into the behavior of the bulk of the eigenvalues of some important random matrices. There are of course many other aspects which are useful and interesting, which I am not going to touch in this talk. For example, how do several random matrices behave jointly? How does the maximum eigenvalue of a random matrix behave? How do the gaps between eigenvalues behave? How can knowledge of these aspects help us to develop procedures to analyze high dimensional data? That is of course the last one is the most important topic which statisticians would be interested in, and I hope that after this talk you will go and explore some of these areas. So, I will introduce random matrices by giving some of the more important random matrices that have been introduced, studied and applied in random matrix literature. One of the first ones that was used is the Wigner matrix. So, a Wigner matrix is simply a symmetric random matrix with IID entries, that means independent identically distributed random variables in its entries, but we impose symmetry on the matrix. So, this is known as the Wigner matrix. It was introduced by Wigner in 1955. The IID matrix, of course, all of us are very familiar and very fond of IID structures. So, a IID matrix would be simply a square matrix all whose entries are independent and identically distributed. The Topless matrix has a very interesting structure. If you look at this matrix, you will see all the diagonals have same values. For example, the first diagonal, the main diagonal has the entry x0, the first diagonal has x1 and so on and so forth. So, this is known as the Topless matrix, and it is connected to the Topless operator in mathematics. It has a very long history in mathematics literature. I think it goes back to early 1900s. Likewise, the Hankel matrix, which is very similar to the Topless matrix, but here instead of the diagonal being equal, the anti-diagonals are equal. So, you can see from the structure of this matrix that the x0 and then x1 and x2 and so on, these are all equal. So, this is also a very important matrix in mathematics. The circulant matrix, if you have worked in design of experiments, you will know the circulant matrix. Here in this matrix, you start with one sequence of variables, in this case x1, x2, xn, you put that in the first row and then you circulate the same variables, these n variables in a specific way to fill up the other rows of the matrix. So, this is known as the circulant matrix. There are more general versions of circulant matrices which I will not go in this lecture. The sample covariance matrix is of course bread and butter for statisticians, and I can define it to be the matrix which is X transpose, where X is an IID matrix. Of course, you can have other structures instead of the IID structures, and this was studied by Wishart in 1928. This is one of the earliest non-trivial random matrices which was studied in much details. The autocovariance matrix is a very important matrix in time series analysis. So, suppose that xt is a real valued mean zero stationary process. Let Rj be the autocovariance between the xt and the xt plus j. The sample autocovariance matrix is defined to be the matrix which uses the estimates of these, and is essentially the estimate of the variance covariance matrix of the first, let us say k many observations. In here it is defined as you take the cross product of these values at lags k and then you take the average. So, it is important to understand this sample covariance matrix also has a Topless structure, but unlike the Topless matrix that was introduced before, this matrix the entries are not independent anymore. It is a very crucial object in time series analysis. Now, let us consider the high dimensional time series models. In this high dimensional time series models, here I am going to focus only on the linear time series models. So, it is very much like the usual time series models. However, what we have is the dimension of this model keeps on increasing. So, formally speaking, xt is a linear combination of the errors epsilons, and shi's are the matrices which are p by p matrices. The errors are of course unobservable, xt is the observable values of p dimensional vectors, and here the catch is that this p, the order of the vector, is also going to infinity with the number of observations. So, that makes it a high dimensional model. The sample autocovariance matrix of order I of these variables xt is given by the similar to the equation that I wrote for the linear time series model. So, you take xt the vector and you take the transpose of that vector and you basically average that. Now, you can observe that for every I there is a different sample autocovariance matrix. So, unlike the real time series model, here I have a whole sequence of sample autocovariance matrices whose dimension is increasing. So, these matrices are non-symmetric matrices except for the case where I equal to 0, and they are notoriously hard to analyze. It is known from the random matrix literature that if you have a non-symmetric matrix, they are very hard to analyze. Usually one resorts to symmetrization and looks at the symmetric version of these matrices. So, as I pointed out towards the beginning of my talk, that in this talk I will focus only on the bulk of the eigenvalues, which means that I am going to look at the entire set of eigenvalues and look at what kind of properties this entire set has, rather than focus on the maximum or the minimum or the extreme values. Here is a couple of technical definitions. So, define the empirical spectral distribution as the spectral distribution which puts mass 1 over n at each of these eigenvalues. So, lambda i's are the eigenvalues of the matrix and you are putting mass 1 over n at each of these points. This is of course a random probability distribution with mass 1 over n at each I. Primary question in this study is how does the empirical spectral distribution Fn behave as n goes to infinity. If there is a limit, then that is called the limiting spectral distribution. It is the weak limit of the empirical spectral distribution, either almost surely or in the probability sense. In non-technical terms, what it really means is I plot the eigenvalues as a histogram, and I would like to see what happens to this histogram as the dimension n becomes large. So, here in the next few slides, I am going to show you a few simulations to show what happens to these specific matrices that I have defined earlier, what happens to the eigenvalue distribution or the empirical spectral distribution of these matrices as the dimension becomes large. So, here is a simulation for the Wigner matrix. So, here I have taken the sample size equal to 400 and I have scaled this Wigner matrix by n to the power minus half. So, this is very much like the scaling in the central limit theorem that many of you have seen earlier. So, without this scaling the eigenvalues will not stabilize. So, once you do that, then here is a plot of these eigenvalues. So, 15 realizations of a 400 by 400 Wigner matrix. So, there are 400 times 15 many eigenvalues, and here is a plot of this set of eigenvalues. As you can see, there is a very nice picture that is emerging out of these eigenvalues. Similarly, if you look at the Topless matrix, here also I have taken n equal to 400, I have also scaled this matrix as before, but unlike the previous slide, here I have plotted all these 15 different realizations in the same graph. So, there are 15 graphs here, and you can see there is a nice stabilization of all of these 15 graphs at the same time. So, in other words, there is from the different across the different realizations the picture stabilizes. So, there is not much of a variation in the graph over the 15 different realizations. This is a simulation of the Hankel matrix. This simulation is very different from the previous two simulations that I have shown you. The difference lies in the bimodal nature of this graph. So, this is a very interesting random matrix whose spectral distribution appears to be bimodal in nature. The circulant matrix gives rise to a very nice picture. We are all aware of the normal distribution, the Gaussian distribution, and from this picture it is apparent that the eigenvalue distribution of the circulant matrix is a bivariate Gaussian distribution. The circulant matrix is a non-symmetric matrix, and hence its eigenvalues can be complex. So, you can think of that as a bivariate distribution, and you can see the nice histogram of the bivariate distribution of a circulant matrix of order 400. The IID matrix gives rise to a very different picture. Again the IID matrix is a non-symmetric matrix, and so its eigenvalues are complex in general. So, it is a bivariate distribution, and you can see from the plot the red indicates that most of these eigenvalues are concentrated on this area, and so one can probably conclude the eigenvalue distribution is uniform on the disk. The S matrix or the sample variance covariance matrix, this is a simulation of that matrix here for the case where n equal to p equal to 400, and I have shown you only one slide here. However, what happens is if you have different pairs of values of n and p where they are not necessarily equal, then the nature of the curve is different, nature of the histogram is different. However, in each case you can see a stabilization. In other words, if you repeat these simulations, you will get the same picture more or less. So, once you have seen all of these simulations, you probably are convinced there are limits existing in all of those cases. So, in the next couple of slides, I am going to describe a little bit about these limits that happen in all of these random matrices I have shown you so far. The scaled circulant matrix, as we have discussed already in the picture, the limiting spectral distribution is complex bivariate Gaussian. For the scaled Wigner matrix, the limiting spectral distribution is what is known as the semicircle law. As you have seen in the picture, the graph looks like a semicircle, even though it is not quite a semicircle, and this is actually the limit density of the Wigner matrix. The scaled IID matrix, the limiting spectral distribution is uniform distribution on the unit disk. For the scaled Hankel and Topless matrices, the limiting spectral distributions exist. However, not many properties of these limits are known. For the autocovariance matrices, if you consider the autocovariance matrix in the real time series case, the limiting spectral distribution is connected to the spectral density of the process. I am not going to describe it here because it is a little complicated to write that down in mathematical terms. The properties of the limiting spectral distribution are not known in closed form. So, that is an open area of research. What exactly is the limiting spectral distribution? One can show that the limiting spectral distribution exists, but one does not know what the actual form is. Likewise, for the high dimensional time series, the limiting spectral distributions for symmetrized autocovariances, recall that here in this case there are many different autocovariances at different lags. For each autocovariance, if you symmetrize them, the limiting spectral distributions of all orders exist. These limiting spectral distributions can be defined in terms of free variables. Unfortunately, free variables are quite difficult to understand for a beginner. So, I cannot go into those, but I have given you references at the end of these slides where you can go and read some of the concepts of free variables. Essentially what it does is tries to generalize the idea of independence which is available for random variables or for the random vectors to variables which are necessarily non-commutative, means that x times y may not be equal to y times x. For example, for matrices, if you have two matrices x and y, x times y may not be equal to y times x. So, the concept of free variables extends the idea of independence, and it is called free independence for non-commutative variables. Here is another area of research. No results are known for the non-symmetrized autocovariance matrices at all. So, that is a very open area of research. For further reading in the theory and applications of random matrices in statistics and other areas, you may consult the books that are listed in the references. So, let us go back to the high dimensional time series models that I had mentioned towards the beginning of my talk, and let us spend a little bit of more time on that. So, the moving average model, the high dimensional moving average model of order q is given by this equation x t equals summation psi j epsilon t minus j, where the epsilons are unobservable, the x t's are observable p dimensional vectors. The epsilon t's are IID with mean 0 and variance covariance matrix IP. The psi j's are p by p non-random coefficient matrices with psi 0 equal to I. You can think of the psi j's as the parameters of the model. So, this is the high dimensional time series model, because I let p go to infinity as the sample size n also becomes large. So, usually the assumption that is made on p and n, the relative orders of growth of these is p over n converges to y, where y is some number between 0 and infinity. However, the case y equal to 0 is left out of this talk, because it is a little bit more complicated than the other cases. The number of matrices q could also be infinite, but that needs additional restrictions on the psi j matrices. Note that the MA0 model is really the IID model, because all the other psi j's vanish and there is only one. So, x t becomes equal to epsilon t, which are given to be IID. Recall we had already defined the autocovariance matrices. So, let us spend a little bit more time on that now. So, the autocovariance matrix of order I of x t is given by x t dash, and you sum over the appropriate number of pairs which are available in the data set. They are of course non-symmetric unless you have I equal to 0. As I already mentioned, the non-symmetric random matrices are notoriously hard to analyze. We shall resort to some kind of additive or multiplicative symmetrization, such as you can think of the products or the sums or several products of several different matrices. We also recall that the empirical spectral distribution was the distribution that was putting equal mass at all the eigenvalues. So, if Rp is a random matrix with lambda i's as the eigenvalues, then the empirical distribution puts mass 1 over p at each of these points. Its cumulative form is given by the number of eigenvalues less than or equal to x. So, that is a distribution function in its own right, and the limiting spectral distribution is the limit of this empirical spectral distribution in some probabilistic sense. Let us look at some of these simulations in this matrix. So, gamma 0 hat is the usual autocovariance of order 0 in the MA0 model, and this is how it looks like. This is really the simulation of the sample variance covariance matrix, because epsilons are IID in this case. In contrast to that, if you look at the lag 1 autocovariance matrix for the MA0 case, then you can see this in these two plots I have taken different combinations of the values of p and n. So, for example, here p is 250 and here p is 500 and n is 500 for both cases, and you can see nice patterns coming up in these two simulations. However, no limiting spectral distribution results are known in these two cases. So, that is a very challenging problem. If we go to model 1 for the MA0 case and look at the product of the ith autocovariance matrix and its transpose for different values of I 1 to up to 4, then you can see virtually all the empirical spectral distributions are identical. That is why you see only one curve. So, it is really the superimposition of 4 different curves which happen to be identical. In contrast to the previous graph, suppose I take the model of lag 1 and I have this x t equals epsilon t plus a p epsilon t minus 1, where A is a suitable matrix. So, in this case I have taken a very simple case where, so it is a diagonal matrix with values 0.5 on the diagonals. And now if you look at the empirical spectral distributions of the same product that I had in the previous slide, now you can see that for u equals 1 the graph is different, and for u equals 2, 3 and 4 the graphs are same. So, now you can see that because of the lag 1 here, one of these graphs gets separate from the rest of them, and hence this can serve as a very nice graphical way of inferring whether the model is of order 0 or whether the model is of order 1. Let us consider the model 3 now, where I take the same MA1 model, however the matrix BP is different from the previous case. In this case also you can see there is a separation of one of the empirical spectral distributions, namely of lag 1, and the other lags u equal to 2, 3 and 4, they are all identical. So, the 3 curves are superimposed, but you can see that the this graph is identical with the graph that was shown in the previous slide, and that is because the empirical spectral distribution of BP and the empirical spectral distribution of AP in the limit they are same. So, what determines the empirical spectral distribution of these gammas is really the nature of these matrices. So, for model 4 I have taken a model of lag 2. So, here is 2 matrices CP and DP. Let us not worry too much about the exact form of these matrices CP and DP, but what is interesting is the graph here, because now you can see the autocovariances of lag 1 and 2 they separate out, whereas because of this model is of order 2, these lags of 2, 3 and 4 they separate out, and they are also equal to each other. So, that is the nature of this graph, the empirical spectral distribution in this model. One can do a lot of simulations, and one can see that similar patterns happen if you use other combinations such as products of 2 matrices or products of 2 and then sum over those 2 matrices and so on and so forth. So, all of these simulations give us a sort of a bird's eye view of the whole theory here. We can do all kinds of symmetrizations. I have shown you slides only for the multiplicative and the additive symmetrizations. One can take more than one matrix at a time. In other words, one can take polynomials of matrices, and one can combine more than one time series. That would be important because you would like to, say for example, test hypothesis between 2 different time series instead of having only one time series. So, that would be a 2 sample problem. And the next question would be, how can these limits be described? I have shown you simulations where you can see this nice empirical spectral distribution convergence graphically at least, but what is the limiting spectral distribution in any of those cases? So, there you need what is the ideas from what is known as the free probability, which is a very technical area. So, I cannot go into that in this talk. One can also study all of these polynomials of matrices in a sort of unified way, and as I showed you at least a little bit of glimpse of this, that you can have statistical applications of these results. So, here is one technical result that I will mention here. More can be found in some of the references that I will give at the end of the talk, and I will point the couple of specific references in that case. So, here are the 2 assumptions on the errors. So, basically these are standard assumptions that are used in many models, where you are basically assuming that the expectations and the variances and the other moments are finite. And here we assume that the psi j parameter matrices satisfy some technical conditions. You need some kind of convergence of these. Then the meta theorem says, or the meta result says, that the limiting spectral distribution of any symmetric polynomial on this in this gamma I star can exist, and we can identify the limit as a function of free variables. Similar results with additional scaling and centering are there when p by n goes to 0. Applications. As I have already shown you, applications to white noise testing, the graphs separate out depending on the lag of the model. So, you can test for white noise, you can test for other hypotheses in very simple cases. There are similar ideas. One can also do significant testing based on the trace of these matrices. As a byproduct of the proofs of the main results in random matrix theory, the trace of any polynomial is asymptotically normal, and this can be used for significant testing for suitable simple versus simple hypothesis involving the coefficient matrices. For further reading in the theory and applications of random matrices in statistics and other areas, please consult the books listed in the references. I might like to point out a couple of those which have links, direct links to high dimensional time series model. This book, for example, is on large covariance and autocovariance matrices and develops all these results that I mentioned towards the end of the talk and shows how to apply them to study high dimensional time series models. This book by Nika and Speicher is on free combinatorics of free probability, and one needs to read this book to understand what is free probability all about. Thank you very much.